All right, today we're going to talk about electrical engineering, the basics. You should really, now is a great time to learn electrical engineering, right? Not only is it fun, I think it's really fun as a focus, as an area of study. You get to make really cool stuff, right? You get to use really cool tools like this Arduino, right? Where you can literally make your own, like AirPods. You can make your own speakers, right? It's pretty cool stuff, right? So, the fundamental aspects of electrical engineering is Ohm's law, right? And it's only 3 letters, which is, each word is 3 letters, right? Because we're only going to be focusing on 3 things, right? Voltage, V for voltage, all right? R for resistance. We're going to put the R here, because like the I that comes up, it's going to be a bit of a curveball. We have I. We have 3 things. Okay? Voltage, the V is for voltage, right, which is pretty straightforward. You've probably heard of the term voltage in the past, right? So what is voltage? It's pretty straightforward. It's kind of insanely straightforward to the point where it's kind of crazy how all these things connect. You'll see how much, like, you start seeing like the ideas of voltage and current and resistance everywhere in life. Everywhere. We'll see it in water. The most famous comparison for voltage and resistance and current and the relationship is water. Because another term where we're going to hear the term, another time we're going to hear the term current, you're going to most likely think of water, not even electricity. You're going to think of water, right? And the reason for that is that currents, resistance, and voltage, they all exist the same way. They all behave very similarly, right? Electricity isn't a fluid, but it behaves like a fluid, right? It flows. That's the whole idea behind it, okay? So voltage, right? We have V for voltage. Let's see. V, voltage. So you've probably heard the term voltage. What is the idea behind it? The idea is that voltage is the electromagnetic pressure. It's the electromotive force, right? Like EMF, which is just like a long way of describing the potential difference between 2 areas, right? And the potential difference between those 2 areas. That's all it means, right? So what does potential difference mean? What's the idea behind that? We commonly compare that to water pressure, right? Like you imagine like a water pressure in a tank, right? In a water tank, or even like in a water balloon. I feel like water balloon is a bit more dynamic, right? Because you can see everything. You can see all the fluid dynamics that happen in the water balloon. Can you imagine like that, right? So the more water you add to the water balloon, right? What happens to the water balloon overall, right? It starts to expand due to the pressure, right? There's more force, there's more collective pressure, and what's happening is you have a higher potential difference in the, you have a lot more water inside the balloon than you have outside, right? So what happens, so what does water want to do? When you have a lot more water inside the water balloon and it's jiggling around, why is it jiggling? And like when you lift it up, it wants to stay down, right? What's happening, right? There's more water inside the balloon, and pressure always wants to equalize, right? High pressure wants to go to low pressure. So voltage is the exact same thing. It's the potential difference that creates like a form of pressure between 2 points. And the greater the voltage is like the greater amount of water in that water balloon, right? Keep adding more and more water, more and more water. Eventually what's happening, it's gonna want to burst, right? So, and it's gonna want to go from like an area of high pressure to an area of low pressure as fast as possible. So that speed, right, the more voltage, and let's say you poke a hole in that water balloon, the more water you add, the more water is going to flow out, right? So that's what current is, right? So we have I for current, right? I for current. I for current, which isn't as straightforward, right? Because you have R for resistance, right? And V for voltage. So it's like, oh, why can't current be C? Well, because C is something else, right? So we'll talk about C in the future, all right? It's not as fun, but it is related. It's all related. It's all fun. Anyways, just wiped it up with my back, but that's okay. So next we're going to talk about current, okay? So, because keep in mind, the reason why we're talking about all this, like, it may be boring, right? It may feel boring at times, but like, you can make really cool stuff. You can make cell phones, right? You can make you can be like the next Bill Gates. You can make a lot of money in electrical engineering, right? And I believe it's one of the fields that is going to be more resistant to AI effects in the job market, right? It's going to be more so used as a tool rather than like a replacement. But anyways, right? You make a lot of money, and I want to say that the most millionaires, like engineers, is like top 10 for that job, like category, like in terms of occurrence, right? Like it's very common, right? So I'm just saying this, even if it doesn't seem important, it is important. I'm trying to make it as straightforward as possible. Okay, so we're gonna talk about currents. So when you imagine the water balloon and it's full of water, right? And you add more and more water, and that water creates more and more pressure on the water balloon, right? Then let's say you poke a hole, right? And then the water's gonna what? It's gonna want to flow out. Flow. That's the whole idea. So that's actually where the C comes in. Not to get too ahead of ourselves, but it's the flow rate of that charge, right? That it's the flow rate of that water coming out of that charge, right? So actually, charge isn't even C. See, well, let's not get it complicated. Okay, it's the flow rate of the charge, right? So the more water you have in a water balloon, what's going to happen? It's going to flow out faster, right? Like if it's like a little bit of water, it's going to dribble out just a little bit, right? Not too much pressure. The pressure difference isn't enough to overcome the resistance, but like we're not going to talk about resistance just yet, right? The pressure difference is only causing enough pressure to force out a little dribble, right? But if you increase the amount of voltage, of the amount of like volume of water in that water balloon, right? I'm repeating things over and over again because this is the only way to learn this stuff. Literally, it's repetition. I'm telling you, it's repetition, right? You just got to do it over and over again, okay? The pressure difference is what? That's the voltage. Like this is the way to learn. Because this is me learning too. I'm like, no, I want to master this stuff because like, at the end of the day, it's electricity, right? I don't want to cause any harm to anybody, and I don't want to get shocked. I want to get shocked as little as possible, right? So, the flow rate, the flow of charge, right? Charge is a separate thing, right? We'll talk about charge in the future. But the flow of the charge, right? Due to the pressure difference, which is caused by the voltage, right? And it's caused, and the way that we get voltage is we multiply it by the resistance. Or the way that we get currents, you multiply by the resistance, right? Resistance. It's super straightforward. All right? Resistance. So the resistance is the water balloon, right? We talked about it a bit earlier, but the resistance is the water balloon. It's the physical water balloon that's holding the water, right? The water is the voltage, right? It's the volume. It's the overall volume that when you increase that volume, you increase the pressure. You're increasing the pressure on what? On the resistor, on the water balloon, on the. You know what was crazy? The craziest thing. I was learning about like I was learning about Ohm's law in class, right? And I'm standing by a lake. So my school happens to have like a really nice like river that like nobody seems to go to because they don't explore. I don't know. I was literally like at the school for like months, and my classmates were like, "Oh man, I didn't even know this was here." I'm like, "Bro, it's like it's behind the cafeteria." But anyways, I'm looking at this river, right? It's like a little stream where animals go by. So I love to go there during breaks between class just to clear my mind. And I'm watching the water flowing through the stream. There's like ducks and stuff, you know. It's pretty cool. So I'm watching the ducks and stuff. I'm looking at the water, and I'm like, oh my goodness, this is just like Ohm's law, right? Where I'm like, the water in the stream is like the the amount of water, right? Because like there's part of it that's dammed off by beavers. Like shout out Canada. I didn't even plan it like this, right? But there's part of the area that's dammed off and holds up like the larger amount of water. And the dammed off area, I'm like, oh, that's the resistor, right? Because like the resistor existing there, it inhibits the flow, right? The whole idea of resistance, it resists the flow. It's straightforward. It resists, right? Like a rubber band can resist electricity because it's a resistor. You know, certain plastics can resist electricity because they're resistors, right? Wood is usually a good resistor, just as examples off the top of my head. But resistors inhibit the flow of the rate. It and resistors inhibit the flow rate of charge, and the charge, the total amount of charge, is the voltage, right? So that's the relationship. So that's the idea, like theoretically, if that makes sense. I think it does. It does make sense. I shouldn't even say that anymore. But that's a little pro tip for you. Like, don't say like, be confident in yourself. Confidence is the biggest thing. Literally, literally, I had a professor. I love this guy. He was great. I had a professor. He was like, I, I, I was like chilling in class, right? And he was like doing like all these numbers like super confidently, right? Because like, here's the thing. Engineering is a lot of math. But math is like the most learnable thing ever. Like people are like, oh man, I can't do it. No, you can't do it yet. You can, math is the most learnable, you just gotta keep doing it, right? Because it's like, it's not impossible. You've had so many other like super nerds like Albert Einstein and like Isaac Newton who did this stuff first, right? So like all you have to do is follow their exact steps and you can literally make $1 million. More than that, right? Like that's all that Elon Musk does, right? He's just like, all right, if this makes sense mathematically, it'll make me more money, and that's why he's rich as hell, literally, right? So, um, electrical engineering is important, right? And so, anyways, I was watching my professor, and like he's doing all this math on the whiteboard, right? I'm gonna wipe this down. Because it's V equals I times R. There is math. But it actually is pretty straightforward. Don't be like, oh man, I can't do it, it's math, I'm dyslexic. No, you can do it, trust. Just like take your time with it, okay? Ohm's law, it's V equals I times R. Okay. V equals I times R. See, that's what the math is. That's literally what the math is. V equals I times R, okay? All you have to do is get really good at finding V, or finding I equals V over R, right? I equals V over R. And R equals V over I. I just like to say Ivor Reviver, right? Ivor Reviver. Ivor I equals V over R, where R equals V over I, and ver, V equals I times R. Super straightforward. If you can learn this math, because that's the basic fundamental of Ohm's law, you can make a lot of money. You can succeed in your electrical engineering course. All right, bye.